Hi, I hope this is clear. You can hear from the Zoom. So last class of this semester and last class of this course, probably to make up. So the goal of today is to talk about what we call allocation mechanism. And the main focus of microeconomics, we usually talk about market, which is the price theory, right? And basically is talking about how the market, buyer or seller, demand, supply, solve their problem within the market, right? Market simply mean there is a price that buyer and seller can look at and try to trade with each other, right? And we also learned from last class, the double auction is also something a little bit more similar. But double auction, you will see the current B&Rs, and then there's also the way, or you look at the standard case auction, is in a way to allocate mechanism. Okay? And the price mechanism or market mechanism works well where we know that it's a large number of buyers and sellers. The reason being that in that case, each individual don't have particular market power, right? We also learned that when there are few firms, then probably we're talking about oligopoly, right? And Carnot or Bertrand would be the result, right? But they are not the only result often observed. And today's class, we will focus on two particular type of mechanisms, how to allocate resources. The first one, the context, that is slightly different from market. It's somewhat similar to auction, but in the sense that in auction, the price you're going to pay is usually only you win, right? If you lose, you don't pay, right? So context is slightly different from that. Is you have to spend some real resources in order to get some probability of winning. The usual case is R&D. Okay, R&D is in order to fight for a new patent, for a new technology, and that is the one that firms should try to do it. Or there is a formal context, right? The competition, right? Say suppose you want to win for Nobel Prize, for certain prize is there, right? The competition, the innovation, the prize. And of course, the problem is how to design this innovation context, right? And that is what we're doing. And similarly, when we talk about the alternative to market, usually it's called about government, right? Government will do planned economy, allocate stuff. But even in planned economy, the problem mainly is information, right? Is you have something to allocate, say who to produce this stuff, right? In particular, in many countries, even they use market economy, they still use allocation by the planner in terms of military contract, right? How to build a tank, how to buy guns, so on and so forth, right? And usually involve a context, right? Because in that case, you have to look for the best object to purchase, right? The procurement, a similar idea. So that's the context. And the next thing we talk about is bargaining, which will cover second half of the class. Is consider a case where you do not have competing, more likely they're collaborating, right? Consider a case where a firm is trying to hire workers. They have to negotiate the wages, right? They're splitting. They try to collaborate. They're not competing, right? Competing, we can use game theory. Of course, collaborating also can use game theory. But they are more collaborative in the sense they try to split the surplus by reaching the contract, right? Because in the contract theory, we cover last week, is the contract is given by the principal. The agent only say yes or no, right? But in general, the contract is not really one-sided, right? It's usually negotiate, right? In some sense, right? So we will consider that. right? It's a lot of supply chain, also the bargaining, right? And even in finance, right, there's also bargaining in the M&A process, right? Among the restructuring, right? When the firm go bankrupt, right? And or capital restructuring, you need to negotiate with people, right? The creditor, the debtor, to negotiate, right? Try to restructure. So this is the bargaining where it kicks in. Okay. So the context is needed when the property right is not very well defined, right? And what happened is when you try to allocate resources, right? You don't have law there, right? It's for the gun design, right? In the old days, right? You have more guns than you have more bread, right? Or in the legal battle, or in some developing country, right? How you can win is to bribe. The more bribe you get, more than you will get likely to win the contract, right? So the one we use is the famous one, is the Tarlock context, the very standard. Okay? And the Tarlock context is very simple. It's a standard game of complete information, the standard version. Of course, you can extend to things you like, right? You can do incomplete information, you can do dynamic, you can do whatever, but the simplest version is this one. Simultaneous move game, complete information, and there's a kick to be divided among many people. For simplicity, we just have two. Okay, it's easy to generalize to any number of n. Okay, and here we make the little bit generalization. Is the value of kick. Okay, there's a one kick there, but is it value by each one is multiplied by the v, right? So you can make vi is 1, then the model becomes very simple, right? You allow asymmetric valuation of the kick, right? The whole kick to agent I is vi, and we assume that this is the case where the kick is not divisible, okay? And only the kick can be just got by someone, okay? So that means that what they are fighting for, by how they fight it is by investment. They invest yi to get a kick, okay? And the cost of making yi, just linear, okay? You can multiply by alpha or constant, but that is the thing, right? There's a standard thing you're trying to do, right? How much you invest to get a kick, okay? And this kick is not divisible, okay? So usually this is often used in political situation where it's an election, right? There's a political rent to get a seat there. People invest in campaign spending, so there's a very standard model. If you look at political economy, okay? But this is the same as R&D, right? R&D will be, this is the value of the patent, they fight for it, right? And that is a very standard model, okay? And this Tarlock context, okay? Although the cake is not divisible, but winning or losing is not deterministic, it's probabilistic, right? Even if you put the most effort, you are not sure to win, okay? And the simplest case is just proportional to the effort, okay? And just yi over the sum of the y's, okay? In more general, you can allow this happen, but in general, you can allow this to happen, that's no problem. Oh, again, the doesn't work, the screen, but anyway, in general, you can make this. Take it to the alpha, okay? You can make alpha in general equal to 1 is like the constant Winton scale, right? If alpha less than 1 is decreasing Winton scale, right? Alpha bigger than 1 is increasing Winton scale, right? But in general, the simplicity, you can just assume alpha equal to 1. And that's the original Tarlock one. Later, people generalize it to a little bit more, okay? And the only troublesome for doing this function is what happens when you have 0 for both, okay? No one invests. The easiest way to think is 1/2, okay? And this also has a continuous, right? If you imagine y is very small, right? and someone go to 0, then it's still continuous, right? In that sense also. And at the very end, we'll give you the foundation for making this proportional probability. Okay, we give you why it makes sense. Okay, and of course there's a micro foundation as well, but we're not doing it here. We are arguing from axiomatic. Okay, but that is a proportion, right? So basically, the model will be each player, the two players, they want to invest in something. Okay, in order to win the price, yi. Cost is yi. Okay, if they don't invest, then it will be 0, right? So that will be half of the price. Okay, and that's a model, right? It's simultaneous proof game. They're easy to solve, right? So let's see how do we solve that one. So for simplicity, let's consider a case where a symmetric case, V1 equal to V2, and we will show that actually is how much they invest is a quarter of the price. Okay, that means that if the investment is wasteful, half of the price actually gone, right? Because two agents actually totally invest half of the price. Only of them get that will be the cost, right? And the total value is just V. The social surplus is just half, right? They reduce by half because of the R&D. Okay. So in some sense, it means that this is what we call rent-seeking behavior. Actually, you will see as the N get more and more, right? And basically the whole rent get exhausted. But later we will see that. But so this, how we prove this is you just take first order derivative, right? This is the differentiate with the probability, right? This is the quotient rule there, and this is the cost. Marginal cost is 1, right? The marginal benefit of investing more is this one, right? It's MR to the MC, and you can solve it out because of symmetry. And you can check this is an equilibrium because you differentiate twice, it's negative, right? And usually in our proof, we didn't talk about SOC, but in your working, you should actually check, right? Although I didn't explicitly do it, because I always argue is contradict, but this one is not contradict, so you have to check. Okay. And what application, as I said, is lobbying, or you have for marketing, is advertising, right? So I spend on this and spend on that, right? And of course, we interpret, right? The P is not the probability, right? The P may be the market share. V will be the size of the market, right? So it's not probability, but the idea is the same, right? Just reinterpret as a market share. Pattern race, right? That is very natural, right? You spend R&D. And spot context, that's what we do, right? And also crowdsourcing. Some of you may or may not know that crowdsourcing is the idea that firm try to outsource it, right? But standard outsource means that you would ask one firm to do it, right? But crowdsourcing is not directly ask a particular person. You just try to ask the general public, I want to solve this problem, okay? Those who solve it, the best one, will get a certain price. Okay, that's called the crowdsourcing, and it's often used in some software or some high-tech or recent stuff because you actually don't know why we want to do that, right? Because you actually don't know who has the talent to do it, right? Just like you want to design in old days, right? You want to design best slogan for certain stuff, right? Then or certain design, you would do the crowdsourcing, right? Do some competition, right? Public competition. That is the same idea. And Bitcoin, right? Why Bitcoin is a context? Some of you may know, right? Bitcoin is how to add a transaction to how to add the block to the chain, right? You have solving a compositional puzzle that is called the proof of work, right? And proof of work is actually you can imagine just simply speaking, you can imagine finding some prime number to solve some problem, right? And it involves solving a very complicated computational puzzle. And those who have more computational power would likely to win. That is the idea, right? Even though you spend the money, then you may not win, right? So that is the you can model it as Bitcoin, right? And actually, look at the recent paper in JFE or JF, and then look at Bitcoin. I mean, they model it as a context. Okay, so that's a very common thing to model that. Okay, and here I want to show you some example. Here is like very interesting thing. Look at the loss system in America and the US, right? And if you know, in British system, if you lost a civil litigation, the loser will pay everything. Okay? If in America, you just pay your own, right? If you win the prize and you pay your own, right? This is if you win, right? If you win, you regardless of win you lose, you pay only your own, right? If you British system, the loser, if you win, you win the same, but you lose, you have to pay everyone, right? Of course, if you win, don't pay, right? So that is the way they look at these two things, a law paper, right? So you can imagine, you can see which system lead to a higher spending, right? Right. So you can check which system is better. Right. And another example you can look at is the fight for property right, right? And you can imagine that there is often there is a patent comes out, and there's a conflict of patent, right? Who actually get the right, and they will fight over that. Or you can imagine there's a player 1 and player 2 are fighting for a merger bidding, right? Bidding for one firm, right? Or two company, right? And from another company fight for the right for fishing, and there's a lobby, right? Very standard. And do note that there's a little bit more funny part is they allow that there's some probability that actually nothing would happen. Okay, so it's not certain that there will be things. Okay, and if player 1 win, there will be no trade, but keep it. If player 2 win, then player 2 actually going to sell it to player 1. Right? So basically, you can imagine player 1 actually value that more. Right? If player 1 win, they keep it. If player 2 win it, actually can sell to player 1 anyway. Right? So that would be the payoff, and then you can also do the calculation. So you can see that can be very general, right? A lot of model can be there, right? To just touch embed, because the model is simple enough, you can see. So that means that you can embed it to any situation that you want to. So that's a good thing about having a simple model. Right, the same model you can just mix and match. Right, you can see I show you how to do some mix and match. And another mix and match thing. Oh, this is solving the model first. Okay, so basically you can imagine this is very simple. This is payoff, right? Once this payoff, right, it's very simple because it's static game of confirmation. Just try to figure out what's the y1 and y2 that maximize it, right? And what here they do is to rewrite that in a big V1 and V2 that makes the math cleaner. But you can just, since you're good at math, right? You can just simply differentiate the guy. You get the solution there, right? That is similar to the standard case, right? So that's why they do that. Okay, and is that okay? I don't need to go by line for this one, right? Right? I don't need to tell you how to differentiate this guy, right? Should be fine. Okay. If you have question, ask me, but I guess that should be fine. Okay. So we can solve it out, right? and turnout is not super complicated, right? And this is the investment is the YI star is there, right? How much firm 1 and firm 2 would invest, and what's probably the winning. Okay, so that is the outcome. Okay, there's nothing very deep here. I'm not going to worry about the math here, but trying to show you that, I mean, even the model slightly more complicated, you can do it. Okay, but I'm not going to go line by line to show you that, because I think we don't have much time to do that. Okay, so we have shown you the 2 players, and in general n players. Okay, in this particular form, no problem. Okay, you can easily solve the closed form solution, as long as you don't even if you have alpha, you can still solve it. There's no problem. Okay, as long as to raise to the same power for everyone, you still solve it. Okay, that's no problem. But when you introduce some asymmetry across players, then you don't have closed form solution. Okay, that's some issue. So that's why you can safely make them the same, right? In the successful, but usually where you would make them different is to make the cost. Okay, you would usually asymmetry. You multiply player 1 by some alpha 1 and alpha 2 in front of y, right? In that case, the model is still tractable. Okay, you would introduce asymmetry on the cost function, not on the probability. Okay, because probability usually, I mean, it's already very complicated. Okay, and do I have in the model here? Oh, in some other model, you also allow that v dependent on the y. Okay, because you can imagine that v is the price to get, right? Maybe you invest more R&D, the price get larger, right? So you allow that to happen, no problem. Okay, but is it tractable? May not be. Okay, but still you can do first order condition, you can do comparative statistics, you can do many stuff. But you can see this model is very useful. Okay, so the same with everyone is 0, you get 1 over n. Okay, so as I said, you can generalize this, okay, to make it alpha. Okay, it depend. Alpha is 1 is constant within the scale. Alpha less than 1 is decreasing within the scale, or diminishing return to your investment, right? And in the literature, it has been shown that if you more than 2, you don't have pure strategy equilibrium, which we hated, right? Because mixed strategy is kind of a complicated. Okay? So that's why usually you up to 2. Okay, and if you really want to 2, more than 2, usually in the literature they focus on the case we call the OP auction, which the case is the extreme case alpha to infinity. What does that mean? It means that the one who invests the most will sure win for sure. Okay, just like you can imagine a context in sport, right? If you run the fastest, then you're number 1, right? But of course, you should allow tie breaking, but tie breaking is trivial because later you will see. Okay? In a symmetric case, then this is non-trivial. Okay, because everyone do the same, then it's likely to have equal. Okay, but later you will see when you have all pay auction, there's no pure strategy equilibrium, only mixed strategy. So the tie breaking rule is not really that matter anyway. Okay, why there are no pure strategy in Nash equilibrium? Okay, we prove it. It's very simple proof. Okay, let's see this. Okay, how do you formally define it? Okay, suppose that n bidders, okay, or n players, they send a sealed bid there, yi. Okay, everyone value as a vi. Oh, sorry. Either small v here or big v here, the same. It's the same as this one. Okay, and if other people are higher than you just lose what you pay for, negative yi. right? So if you are not the lowest, so not the highest, then you just pay your bid. If you're highest, depending on how many higher than you, sorry, same as you, then you just share this number of people actually same as you do, right? And just this, okay? That's rather standard model, right? And now we try to look at the case very simple. Look at the two-person case because the proof are generally the same, okay? We just make our life easier. Okay, everything is symmetric, right? If you're the higher than the other, you get the V and minus what you pay. And if you're the same, equal minus what you pay, and this you sunk, right? So Y is sunk, okay? Same as the context, okay? The only difference is this two, right? The payoff, right? The payoff is always, you only get something only if you're the best, okay? Basically, that means winners take all, right? The one who win get everything, right? The one that win the game, okay? And that's actually what happened, right? When you go to job market, right? There's a position there, right? And only the one who published the most or the most attractive guy can get a job, right? So if you are slightly below, then you lose, right? Suppose a guy published top 5 or top 3 A journal. You have 5 A journal, okay? You have 4 A journal plus say B plus journal, then you can't get a job. No matter how well you're doing, you just one position, right? You lose, then you lose. No matter how close you are, okay? So, but that's life, right? Winner takes all. Okay, but that is what this try to model. Okay, we try to argue that there's no pure strategy. We'll prove it. It's very simple proof. Let's do it. Okay. Now, first is it's easy to see it's strictly dominated to bid more than V, right? Because the best you do is V, right? You bid strictly more than V will be negative. So that is strictly dominated by 0, bidding 0, right? Bidding 0 for sure is 0. Okay. Second, okay, if your I play I, you bid no more than J, okay? So basically you lose or you get half of that, right? But if you bid slightly more than the opponent, then you get the whole, right? The surplus increase. Is that clear? So make it simple. Suppose the V is $10, okay? Your opponent is bidding 8, okay? You're bidding less than 8 or equal to 8, right? You bid less than 8, you lose, obvious, right? If you bid 8, then you share, right? You pay 8, but you're losing in negative, right? But you bid 8.1 or 8.01, right? Then you win with some surplus, right? Same for whatever value you're looking at, okay? And in the case, is everyone the same? Then everyone have negative payoff, right? Because you only get half of the surplus, but you pay the whole thing, right? It's half of that, right? But you can see the tie-breaking rule doesn't really, whether it's half or you get 1/3 or you favor one guy doesn't mean all the argument holds, right? Doesn't rely on equally split when they're the same, right? But the argument work, okay? And now we try to prove one thing, okay? Where a mixed strategy equilibrium, where each player randomized over from 0 to V, okay? And we try to prove that this is actually a Nash equilibrium, okay? And remember how we prove a Nash equilibrium is to assume your opponent adopt an equilibrium strategy. You try to see whether you want to deviate, right? You calculate what is your payoff, okay? So suppose player 1 actually follow the equilibrium strategy, right? Where he is uniformly from 0 to V, right? And that means that his CDF can be characterized by this one, right? Because because like this, right? It's uniform from CO to V, right? It's uniform from CO to V. There's CO to V here, right? So the height is 1 over V, right? The CDF is just the integration, right? The integration of this area is just this function, right? T over V, right? Because it's the area, right? It's just T is the bottom, right? T times 1 over V, right? So that is the function, the CDF, right? That's uniform, right? Now, let's look at the payoff of player 2, okay? And we can show that in this case, player 2, no matter what he do, actually pay off 0. Okay? This is similar to rock, paper, scissors, right? If the opponent did rock, paper, and scissors, I did rock, paper, and scissors because there's no way I can gain from that, right? Same here, okay? You can check, you take payoff 2, right? Is the probability to win minus y2. I don't make equal because equal has there's no, the probability will be 0, right? Okay, right? Probability equal to that number is 0. It's continuous, right? So I can do that, right? And for any y2 you pick, will be just put that there, right? You're higher than that, right? You win if this is you're higher than the y1, right? And you can check, right? Put it there, y2 over v, right? Minus v, and you can easily see multiply. Yeah, sorry, multiply. Yeah, sorry for a typo. Let's multiply, right? So it's y2 minus y2, which is 0. So which means that for player 2, no matter which point he picked, whether he picks 0 up to any point will be 0, right? So he can well uniformly, that's fine, right? So means that there are no deviation because no matter which point he picked will be 0. This is simply just rock, paper, and scissors, right? The other guy is randomizing rock, paper, and scissors. No matter what I do, same payoff, right? Same here, okay? So that's why this is one equilibrium. Of course, there are many. In this case, they actually been shown there's no other mixed strategy, okay, in this particular example. So basically, just where everyone is that randomized over CO to V, okay? So that is very simple, right? And this make your life very easy, right? Because you know your strategy, you can calculate expected payoff, right? In particular, you look at this in this all pay auction. No people expect to gain anything. Expected payoff is 0, right? So all pay auction make your life very easy, right? Because you can imagine they are doing R&D game, and you can see how much R&D if the market efficient is. Every firm spend all randomizing over resources, right? In that case, on expectation, there's no rent is left over, right? And just like Bertrand, right? Not realistic, but it's just like things is getting more easy to calculate, right? You can easily check out. And that's not surprising, right? You can imagine this is the case where in the old days, when we see the share bike in a few years ago, right? In the time that 共享单车, right? Everywhere in China, everywhere in the world, right? They spend all the resources in order to become the market leader, which is a V, right? But turn out that everyone got over competition. They all got burned out and they all lose money, right? And similarly, look at recently the new energy car in China, right? Actually, many people spend so much resources. I mean, billions of $billion put there, right? Because in order to be you only to become the winner, right? It's not divisible, right? Only you become the winner is economic scale, right? Because there's economic scale there, right? You need to have big enough economic scale in order to make profit, right? Because you need to make sure that there's enough charging station, a lot of stuff there to make sure that it's viable, right? Why only left Tesla, right, is so profitable because you need economy scale, right? But anyway, I hope that justify that. Now, I'll probably ask, is there any other form that competition that is doable? Yes, there are other way to do it, but they are not as common as you see Talot, right? The Talot is say common to every, when you talk about context, it's almost likely either the all-pay auction or the one I mentioned, right? Or the reason is not because they're most realistic. Well, of course, there's some element there, but the alternative is not nice, but when you take the differentiation, it's very complicated. So that's why it's not very popular. But still, we can do it. There's some paper doing it. So the first one is logit, right? Logit is very common when you do regression, right? So you can imagine that is proportional to that. But when you run regression, that's good, right? Imagine that you're looking at the data of R&D. You plug in this one regression. You're not looking at the closed form solution, right? Then you run regression. That's good, right? Because this is exactly what you expect, right? Y can be measured by some data, right? You can put a regression model there, y equal to beta 1, beta 2, beta 1x, and right, and so on, so forth, right? You can do that, run a simple regression, right? And the other form is you only if a two guy, right? You can look at probability one wins depend on this, the difference, okay? And some increasing function, right? This phi can be different from the phi above, but any function would do if only 2%, right? And this will work, right? You can justify according to your situation what should be the phi, right? Can be log, can be whatever function, exponential, can be square, whatever, as long as it can make sense, right? But these are the model that you can use, and they have been seen in the literature justified. Okay, so you can do that. I think it's very useful when you try to put it in your application, especially for people who are doing environmental study or doing M&A fights, right? That is something very natural. Or Bitcoin, right? That will be easy to see. Okay. Lastly, before the break, I want to tell you how would you justify the Talot context function. Okay, that is how the literature justify, and how you would justify if you want to impose something new. Okay, of course, there's a lot of things in the literature have been proved. Okay, but you may ask, some of my research is basically doing this type of style. Okay, and what this style is called axiomatic style. Okay, what axiomatic word is saying is slightly different from game theory, right? Game theory is saying that, okay, we assume how people behave. There's a rationality, and then we define what is solution, right? And that we analyze that, right? But here we are instead don't talk about agent, we talk about the solution directly, right? What is the appropriate solution concept, okay? Right? We're not talking about how they arrive it, okay? Actually, that's what we talk about the cooperative game. We talk about at the end of the day, we talk about bargaining, right? What is the bargaining result that's reasonable? We don't talk about how they arrive the bargaining. We don't model the process. We model at the end, what is the acceptable end outcome, okay? So here is, we don't give the foundation. There is a paper as well, but you can give a foundation why the context would end up in this probability. You can model that, okay? You can model a dynamic game, how this thing ends up in there, right? Maybe you can imagine there's a tug of war, right? There's some foundation you can do, but in this thing, we do a reduced form. You can imagine that axiomatic way is a reduced form, right? And the non-cooperative way is a structural form, right? Sometimes reduced form is better. Sometimes other way is better, okay? Axiomatic means we don't have to rely on the particular structure to make it work. Okay, later you see that's why Nash bargaining is very common, because it doesn't rely on particular structure of bargaining. Okay, as long as the solution satisfies certain thing, that's fine. So now let me talk about how we do it. Okay. So this problem, you can imagine that as an n person, okay? They have effort, okay? Do note that the effort now become exogenous. It's a part of the input of the system, okay? We don't consider people choosing the effort. We are thinking about after they choose the effort, how would the outcome would like to be, okay? We expect people spend effort, and what should be the outcome, okay? There's n players, and the outcome is pi of y. So here the model is like this, okay? When you do axiomatic, always have two things. Define what's the input, what's the output, okay? The function is there, okay? And the input here is just y, and output is just p, okay? You have to decide what is the appropriate way to assign p, okay? And of course, there are many ways, right? The only restriction is, the first way we put it is, it must be non-negative, must add to 1, right? So that's probability. I think this one's trivial, right? This one's trivial. Okay, we will impose that. Okay. The second one we impose is saying that if someone spends more effort, he's more likely to win. Fair, right? It's not going to be harmful. It's not saying that, okay, in the other case, right? When several boys try to date a girl, right? Usually, more money or more handsome would work, right? But sometimes may not, right? Maybe the girl said, oh, maybe he's too handsome, he has too much money, I feel insecure. No, we don't allow that to happen. More money, always better. Not sure win, but always better than less money, okay? And to your competitor, it must be the case if the other guy, your competitor getting more money or spend more effort, you cannot get better. There's no complementarity. You're competing. Okay. I think this is A2 is also very natural. It's fair, right? The third one is slightly, I think it's reasonable, but may not applicable for most cases. But this is saying that if we swap guy number 1 and 2, okay, swap the effort, the probability also swap. Okay, you just call number 1. Number 2, call number 2, number 1, swap their effort to be the same. So there's no particular treatment to particular guy. Okay, that doesn't matter, right? But in some cases it's not, right? You can imagine that in the case where when the firm competing for R&D, right, or competing for litigation or what, some have default winner or some is more favorable, right? Maybe it's incumbent or some reason is more favorable. Okay. But here we just make anonymity. Okay? The assumption is you swap thing, the name of the agent doesn't change the outcome, P, right? This simply means the value determine Y determine the P, right? It's not the order of Y, right? Just means say for example, my effort is 1, your effort is 2. I'm number 1 guy, I'm number 2 guy. Okay. In that case, my probability win may be 1/3, you're 2/3. Okay? Suppose I swap our output, swap our input, then our P also swap. Okay? That's what you mean. I think this 3 is trivial. Okay? Now, here comes somewhat, the next 2 is a little bit tricky. Okay? Okay? So that is require what we call the subcontext. Okay, it related to what we call conditional probability. Okay, suppose 4 of us are competing. Okay, and with some probability there. Okay, now suppose we know that I'm not winning. Okay, for some reason you know I'm not winning. Okay, only you guys are winning. Okay, or only you guys are competing. Okay, your effort. You guys' effort win the same. Okay, what should be the probability in the smaller context? Okay, it should be following the Bayes rule, consistency. Okay, so basically, what this axiom actually means that if I tell you how I solve 2-person context, it gives some restriction how we solve the 3-person one, right? Because it has to be solved inconsistently. Suppose knowing that I'm not winning, only you guys compete, right? So then you will be, how much you like to win depends on okay? The proportional to the bigger context, okay? So that respect to M smaller set, right, will be base updating, right? Just adding up all the people who win the M over original, right? That's the base rule, right? It's basically only M people are competing. We just cut out me, you just compete, okay? Is that okay? So suppose in this way, okay? We have 4 people here, okay? Originally, my winning probability is 1/2, okay? You two maybe 1/6, 1/6, 1/6, okay? No, is yeah, 1/6, 1/6, 1/6, right? 1/6, 1/6, 1/6, 1/2, right? So right? And after I'm gone, you guys play. You're still doing the effort, right? Then you will be 1/3, 1/3, 1/3, right? So the same, right? So that's proportional to the original probability, even you reduce, okay? And the last one is independence, okay? It means that regardless of, in the smaller one, regardless of how much I do, doesn't really relate it, okay? Just like independent, right? Basically, these two jointly imply that you can build from the small, if I tell you how you compete for 2 guys, you can build from this next one. So this is more like standard thing when you consider axiomatic work, is we know how we solve in some situation. We use axiom to extend our knowledge to bigger, okay? Suppose we know how to solve 1 versus 1, right? And we can easily extend based on this assumption because, right, we know how to solve 1, we know put some restriction on the others, right? That's usually how you try to figure that out. So the axiomatic work, I'm not going to bother you with that, I just give you some taste, is usually what you do is you will have to show these axioms as a if and only if. Of course, it's easy to show that what you want to do satisfy all the axioms. But of course, the key difficulty is going the other way around, which means that only this satisfy the axioms. So this means that if the axioms are acceptable, that's what we have. That's where uniqueness is important, right? This axiom imply that, and this imply axiom. Okay, so there's a proof. Of course, the proof is very complicated. I'm not going to bother you with that. It's only, I think this only they figured out that in 20 years ago in the EP, but after that this is the axiom there, right? So there's just proof some F there, okay? But this is not yet the talon, right? And you need to put some homogeneity, okay? Which means that if you multiply everyone, you double everyone's effort, same, the pair the same, right? So you half the same. So and you can prove actually is the a generalized talon raised to the power m, right? If you have in constant with the scale, then you just then you just get the same, right? So that would be the way to prove the axiomatic work. And axiomatic work is very useful because sometimes strategic may not be the best way to solve the problem, right? Because you can imagine that for environmental issue, right? I sometimes want to achieve certain target outcome. What outcome I want to, how to allocate things. I have some normative axioms. I want to impose what outcome are acceptable, and then tell us what rule we have, right? Same as in the finance, we want to have some banking or rating or whatever, right? We have some desired outcome, right? And then we can tell what input output I can calculate the rating or so on and so forth. These are the model that is there, right? And many indexes we see in the world is actually should have some foundation for that, right? So H index for citation and then many things actually has foundation for those. Okay, and This is the last slide. Maybe let me finish it before the break. Okay. So if you have another way, it's called the difference. Before it's like multiply by same. Now I said everyone just have see more unit money. Okay, constant adding. What you get is the logistic. So now you can see which one is more reasonable. I don't know, right? Because this is say this is saying that more like the money, right? You spend $1 more every month, maybe the same. Maybe say every the return to this is 1 to 1, right? But this one is looks like more like the scale of competition, right? Right. So is that it really depends on which one you think that is more appropriate. And as I said, this is the one that you see most often. Okay. But the other one also you can do it. And sometimes maybe easier to do it in regression, but the other one also easy, right? It's not something complicated as well, right? So I hope that now I am done with the context, and I told you that I have many applications, and the model is very simple enough to plug in into the multi-stage model, right? You can imagine that firm competing to become the supplier or the seller, and so on and so forth. They compete, and then go on, so on and so forth, right? Maybe because M&A, two firms fight each other. After they fight, and they will have product competition, right? Whether they win, they're different, right? Or there are many things you can imagine in this model, right? By allowing this thing to happen. Okay, but you also illustrate the idea how you can solve this type of direct context, right? Not through the market, right? But through some effort. Okay. So let's have a break of 15 minutes and come back. We'll talk about bargaining. You can see we are very ambitious. The bargain is very long. So, but there's actually two parts, right? The complicated bargaining and summarized bargaining and many things. Okay. But let's talk about that after 15 minutes. So we'll resume at 3:38. We'll resume at 3:38.
记录放进去，放进去什么呢？放进去需要一个很复杂的计算，但是很复杂的计算呢，点在你要做的，因为这是很便宜的话，这个把人就给我选择我在上水来，在编一个系统的时候编，所以说你这个放进去，就所谓的传在什么呢？非常高。那 cost 的话，它怎么保证这个东西呢？所以说，我估计我不买东西，但是我觉得未来差一点东西，我就挖矿，就是说如果挖成功了，然后所以我才愿意去加入这个东西。因为你挖矿不得挖大，挖给他的没有一个。电啊，上面。电脑的钱，那钱电不会的，会的，会他们都建在什么手刹上面，还有。写算力不做这个可以干的事情，现在算力的就是第一年的在回来就很多大数据啊，这个比较还是很多自己的，这个块儿其他的发一点。开始黑的，日本做的黑的很简单，很简单，很简单。之前其实很多都在做这个东西，做这个机器，但是比较杀之前提出来有些用的 content 很难去把这个成本加进去，所以才做了这个东西才可以比赛出来。不太比赛出来，它有比赛出来是吗？是没有一个人去编这个的，所以比较有趣。这是不是今天要讲的？你说这个 money 对吧？我给你看，我教另外一门课有一个。Cryptocurrency。这个就本冲那个了。然后 ，this is the JLE paper, and you can read this John O'Hara this paper. This paper is more reviewed. After reading this, you know what it's called. Economics. Of course, econ is very complicated when you look at the technical side. You can, I suggest if you try to read again, read this one first. And once you read this, you go back to the other paper. Once you do that, you can do the economics. The older has no economics. This one has some economics. Of course, impact. Yeah. It's another thinking like the future. 能够维持不行的，不理解存在兄弟的，我跟你故事可能对他本来没有喜欢，但是在这个时候，你说你但是不是，因为他因为是比较不过我不能 stay 不着了。
我感觉他整个东西都是靠人们在实践，然后人们会相信他有发力来实现，所以我感觉他本质上来说就很像是一个发力。
对，包括因为它的计算还是有计算电还是，所以马斯克说的有太阳能的话应该是那太阳能解决问题的话，来推荐的吧。到我都是好几年来的，主要说是这几次，然后在上面，现在有网课的时候在山上，说是这样。在网课的时候在山上，上学的回到大学，后来说是经济。这个在
我也了解，就是这种做到现场实习，但是我想说就是可能有一些新的元素会有新的，这个过程之前没有考虑到的情况，比如说我们在考虑利用，然后可能我们就考虑过往的教育背景。那假如现在出现了一种新的形式，就是能够作为信号的东西，那我们就考虑它了，就是它会不会产生一个对，就是人们对非欧能力的期待值的膨胀。对，然后你想说这种的话要怎么去解决？
这个我觉得他有一个，这个是在质量上的他的投入，做这些，因为你怎么说他这个技能上面这个方面还是比较先有我们做的活动啊，都搞很多。金沙就搞很多，还没搞办法，这个就更大有没有？
那是说的这个突然让很难听懂，不知道为什么感觉就带有口音一样。
其实澳门、新广州啊、深圳略有不一样。但其实北京这个语言跟其他地方不一样，不一样。大概电我是不一样，就高级的低级的，常规的叫高的，而且词汇不一样。词汇起伏也高，对，天龙国的就跟天龙国的，上海的，对不对？ 听不懂，对，我觉得这方这种很好吃啊，中华就很好吃。
中华最远了。
会比较高了。
有一个站。
中华都坐过船，对不对？中华就就是那个南部方法。
这个啥呀？因为我那时候我也没去过。那个我。
都对。
但是会有时间先后嘛，就比如说这两年3个月吗？3个月就早就他们现在是丰富了，可能以前那块的
对，这个
他可能只是
把记录下来，包括青海国家的，对啊，真的。
中国人。
你自己看的，你自己看数据嘛，对吧？不说我们不说啥了，我们只看数据。
So now let's continue bargaining, which I was one of my research topic when I was a master student, and I still doing this these days. So hopefully I can still do that, but it's getting more increasingly technical these days, this field. But when you apply, you still have a lot of fun, okay? Because so simple, the idea. Okay. So let's talk about bargaining. Okay. The classical, there's actually two approaches to bargaining. Okay. And both of them are actually done by Nash. Okay. And probably the first one, you notice, actually you look at the literature, a lot of people call Nash bargaining, right? Nash bargaining simply is, later you will see what do you mean by Nash bargaining. But Nash bargaining is, if you talk about the simplest case, it's just basically it's a $1 split between two guys. The standard thing is just an equal share split, okay? And that's make everything is very easy, right? But later you will see it's slightly more than half, splitting half, slightly more complicated, but the simplest case is splitting the half. And there are two other concepts that related is called Kalai-Moninsky, or the Kalai 997 is called utilitarian. There are two other concepts. There are way more than that, okay? And the literature more than a dozen of ways to do it. But you will often see the Nash bargaining is the one that often used. First is because it's easy to solve, okay? That is very important. And second, later you will see there are ways to justify it. There are micro foundation that is coming from what we call Nash, actually justified, we call the Nash bargaining game. Yeah. And later, the Nash bargaining game is a simultaneous move game, it's not a game. Okay. And turn out that we can do a dynamic game. Okay. Actually have a bargaining process in the sense that one player propose and the other guy accept or not, and then the other guy could counter offer. Okay. And you can go many period or infinite period. Okay. And this is called Rubinstein bargaining. Okay. And then can justify Nash bargaining. So that's why Nash bargaining has a lot of people using it, because that's a good foundation for that. Okay. Okay. And okay. So since the literature starts with Nash, so we do the Nash. So the next bargain is axiomatic way, as I said before the break, right? Basically, just like we don't consider what is bargaining process, we consider what is the rational, what is the reasonable bargaining outcome, right? What is the reasonable outcome that we should see? Okay, let's consider the two-person problem, and more will be very similar. More than N will be similar because if we don't care about the process, right, just the outcome. So it doesn't really matter how we. It's very simple to generalize. Okay. So let's look at this. Okay. So we start with talking about the case of what we call the feasible set. Okay. Feasible set is what are the possible outcomes they can do. Okay, that's the input of the model. Okay, because we talk about the bargaining, we talk about what they can do. Right? They can do is a feasible set. Usually you denote that as a real number. Okay. Guy number one get what? Guy number two get what? Represented by number. You can imagine utility, right? So it's a vector x, x1, x2. Okay. You can imagine that all possible agreement they can reach can be represented by a number, right? If you try to draw a graph, it will be like this, right? Let me draw it here. Usually that's what will show you x1, x2, right? What they or u1, u2 depends on how you like to represent utility number or the money, right? So that we just like anything can be achievable, right? The set there, if they try to bargain, they bargain over the outcome over this set, right? That's called the feasible set. Okay, can be very general. Okay, and if they are going to share a pie of size 1, so what does that mean? If they do this in particular, this is what you get. Okay, x1, x2, just a line of 1 and 1, right? Assume 3 decomposable. If they cannot throw away the thing, there's the line. If they can throw away the ink, then will be just this triangle. Okay. This is the thing, right? What they can do together is called feasible set. Okay. And next thing is to get the bargain. We have to model outside option. Okay. Outside option means what if they can't agree, what they would do is D1, D2, can be anything. Okay. Usually 0, but D1, D2 can represent what they can do by themselves without collaboration. Okay. Usually it's co-opposite option, but usually we make it 0. Right? But this is important. This is agreement point because it will affect the solution. Right? Because this is x1 minus d1 is the gain from bargaining. Right? And x2 minus d2 is the gain for player 2's gain from bargaining. Right? We only allow a point, we don't allow a set here. Okay? So do note that we only allow, say, in this way, right? Look at the previous case, right? This is the point. The D can be here, the D can be here, the D can be anywhere. Okay, of course, if the D is right here, then you don't have the bargaining breaks down, right? But that's the model. Is that clear? We have set of outcome and discipline point. Okay, these two are basically the primitive for the model. So this is the input. Okay, this is the input. And so it's a little bit more complicated. We allow the preference. So we allow some u1 over x1 and u2 over x2. But you can simply assume u1 depending on how you like the model structure. So assume the utility. Okay. But you can just assume directly utility at the beginning of the feasible set. The same thing. Okay. And you also put the payoff at this agreement point. So you can either assume utility right away, or you can assume one more layer, the outcome there, and utility over outcome. The same thing. Is that clear? Okay. But that is the model. Okay. Okay, and later you will see why we have utility, because this is what the next thing. Okay, so now we have to define what's the bargaining problem. Okay, the bargaining problem is U is utility, right? Give me a pair of number. Okay, what is set, right? Set of numbers, set of the utility they can achieve by themselves, and at one particular point that is belong to the set. Okay, these belong to the set U. Okay, very important, right? And this U is compact and convex. Okay, and convex is important. Okay, and actually our dean, there's a paper in Economica, try to do the bargaining without convexity. Okay, you know what the convex means, right? Convex means if you take any 2 points in the 2-dimensional case, right? Anything in middle also in there. Okay, so that means that just go back to here. In this one, this is not convex. Why? Because I picked this point and this point, it's not there, right? So convex, it just means that I would connect all the points there. Okay. The problem asked, is it very restrictive for the convex? In some sense, yes, but that's okay. We need to make assumption somewhere to get the solution, right? It's approximation anyway, right? We don't expect our model to hold exactly in the real world, but that. And we assume there exists some outcome that is better for everyone compared to the discriminant point, right? It's not so strict, right? So everyone, there's an outcome that everyone would prefer, strictly prefer to the D. Okay? No one is indifferent between the outcome, right? Okay. So what's bargaining problem? Bargaining problem is for each solution is for every problem, I can tell you what they can get. Okay? So it's a fun. The input is the bargaining problem. I tell you the solution. Okay? For every bargaining problem, I have a solution. Okay? And how we can map this, right? There's an input and output, right? And we try to make sense what the F should be, what's a reasonable F, right? We want to find a universal F that consistently, no matter how you change the problem, we tell you what the solution. Okay? Is that clear what we're doing? So we're bargaining solution means that I tell you what they can do, they collaborate, get U. If they don't collaborate, get D. You give me these two information, I tell you what might be the bargaining outcome. Okay? And do note that it's a function, not a correspondent. So I tell a particular point there. It's not, there's a unique solution there. Okay? I'll tell you, pinpoint you what number I give you. Okay? I tell you what they collaborate. Okay? Do note that I can map to D. Right? D is allowed. I can tell you they can map to D. Right? There's no problem. Right? In this model, I don't restrict anything. Right? D is belong to U, is anything. Okay? So now, is that okay? So now we understand what we're doing, right? So now, how do we solve this problem? Okay, is the highest goal in axiomatic study or like this kind of work is trying to say, I impose the constraint on F. Okay, so that I have only one solution. Okay, and the first restriction, I think, is somewhat reasonable, but is that there are no money left on the table. Okay, so that means that the outcome should not be the case that either we that Pareto dominates our solution. Okay, that means the following. Okay, let me draw this. Okay, suppose there's a convex, right? There's U1, U2, because we don't need to talk about X, right? Right. Suppose I have a U is a convex, so that's something like this is fine. Right. So just like this, maybe. right? Maybe this, right? So priority optimal means that it must be in the frontier on the northeast direction. So I can be anything here is fine. Okay. Right? And everything other place will not. So Pareto optimal means I will always pick the northwest frontier. Okay? Is that clear? Right? Because you can imagine, right, why there's something we can do it, but we don't do it. All right? Must be some reason we don't do it, but in this model we don't allow, right? We just don't want to throw the money on outside. Okay? But of course, if you learn game theory deep enough, there's some reason that you actually cannot achieve efficiency. Right? Actually, prison dilemma is the classical example. You cannot achieve this one. Right? But we assume because they're collaborating, they're able to solve the problem. Efficiency is there, right? Pareto optimality, right? Because when they talk, they're able to agree, right? Because in this model, we assume once they bargain, they're able to sign a contract that's binding, right? So no one can deviate. So they avoid the problem of prisoner dilemma, right? They can sign a contract. Okay, so that is the background behind it, right? The second one, I think that one is also very simple, right? If I change 1 and 2, what their U and D's are, the solution should be also swapped, right? If I call 1 is 2, 2 is 1, same, right? So I change the problem, flip number 1 and 2, the solution also flip 1 and 2. Okay, I think that is not very controversial, right? PO and this not very controversial. Now, this one is okay, not very controversial, I would say, right? Because we have utility representation, right? So I have some affine transformation, right? Multiplied by something and plus something for everyone, right? And also transform my disagreement point. Okay, the solution is just do the same transformation. Okay, so I don't know whether you like it, but that is what we are doing, right? If you talk about utility, that may make sense, right? But if not, then may not always make sense. Okay, but in general, this is not people complain about. This one is okay. It's not something too terrible. Okay, so the first 3 axiom is fine. Usually not many people complain. The most people complain is IIA. Okay, the I is the following. Okay, it's the most controversial thing is if you cut out the thing that is not in the solution, same. What do I mean by that? Okay, so I have a problem U and D and a smaller set. As long as the solution of this is inside the smaller set, solution same. What do you mean by that? Okay, let's look at this one. Another one, okay? Suppose I have U1 and U2 here, okay? And suppose I have this as our outcome, okay? Now, suppose the bargaining solution is this guy, take this one, particular, right? And that means that as long as I have another set that include the old solution, is complete within, okay? So suppose like this. Okay? The blue one, the solution still is the orange one. I shrink what they can do as long as it still include old solution, it's the same. Okay? Just think the following. Now we can do a lot of stuff. Okay? And suppose we agree on option A. Okay? And we can do A, B, C, D, F, G, H, I, J, K. Okay, suppose originally. Now I said, since we don't choose K, kick it out. Let's consider A, B, C, D, E, F, G. We should still choose A. Okay, we kick away the thing that we didn't choose. Should be the same. So put it this way. Okay, let me think it this way. Okay, suppose now we bargain. We go to a picnic. Okay, we can go to Shenzhen, we can go to Japan, we can go to Taiwan, we can go to USA, we can go to Israel, we can go to Russia. Okay? For example, this is for our Christmas holiday. Okay? And now, suppose now we say, okay, we are going to choose maybe Japan, say, for example. Russia is not in our list, right? So now we consider, we bargain again. Take away Russia out. Just Shenzhen, Japan, Taiwan, and US without Russia, right? You should still choose Japan. I shrink the set, the original solution is still there, right? You should still choose Japan, right? Whether you choose Japan should not be dependent on whether Russia is there. Fair enough. It's controversial in the sense that actually, in the real world, that actually it matters. It matters. You choose this because maybe you argue that why controversial? I choose this because maybe I'm able to do that. That's why maybe this is chosen because I have a lot of opportunity here. Right? Although it's not relevant, you cut it out, that's very different. Right? So actually there's a lot of case in the choice theory. When you have transitive preference, that's a problem. Right? When you choose A and B, you choose A. B and C, you choose B. But A and C, you may choose C. Right? The same idea here. Right? Actually, it's related to transitivity in some sense. Right? The presence of, and in bargaining, that's a problem. Because I may argue this is allowed because a lot of opportunity that one can do better here. Right? When I shrink, actually one is not so good. I should favor two more. Right? I mean, that is something that may be reasonable to think about, right? So that is controversial. And of course, that is the reason why people don't really like it. And try to do away with that and see what kind of outcome you may get. Okay, as I said, because bargaining is so common, there are more than dozens or even several dozens of bargaining outcomes. How to model bargaining. Okay, but the next one is still the one. Of course, this is most natural you would imagine. Very natural, right? Things relevant is not there. It doesn't really matter. But in many cases, it matters, right? The irrelevant thing might matter because irrelevant thing actually can represent how good I am, right? I have many ways that actually I'm good, right? But that actually justify I get that much, okay? Anyway, so let's now talk about what the Nash does, okay? In his, I think, one-page of proof, math proof, he proved the following, which is very surprising if you first time see this kind of proof, is he just had 4 axioms. Turn out that what is the solution there? You just maximize the product of the net surplus. Super surprising. What the outcome is, you find the V in the U such that they maximize the product of the utility. Completely out of blue. Right? It's just like, what? How can you prove that? It's like a magic. Okay? I'm not going to show you the proof. You can try to read that. It's just, given your math, you can be able to read it. It's not something complicated. There's some genius step there, but the math is not complicated. It requires some genius to think, right? But I'm not going to do it. But it's very surprising, okay? Because it simply means the following, right? It simply means that you try to draw it, right? You just try to draw an indifference curve. and that's where the touch. All right. Suppose D1 and D2 is 0, and just a curve there. Parabola, hyperbola, just fit it. Right? Very interesting outcome. Okay. And of course, the hard part is to show you that why this if and only if, but that is beyond the scope of our class because none of you doing any proof anyway. You will just need to know this formulation, this formula, that's how you solve the model, right? Because in general, right, you will solve this problem in a much bigger model, right? And then you will tell what's the V come from the other part of the model, and D come from the other model, right? You can just find what's the V there, put in there, then you're done, right? Because in this ring, it's choosing V, right? Right? But in general, maybe this V is a function of something, then just do as well, right? V maybe depend on quantity they produce, right? Just find out the quantity, then maximize the both. Okay? So do note that when you apply nest bargaining, it have to be, remember the U must be a convex complex. Okay? If not, then you cannot simply impose nest bargaining. But usually you're splitting money, right? Which is an I, right? Then there's no problem, right? It's compact and convex. Oh, I forgot to define compact, right? Convex is fine, right? And if you talk about Euclidean thing, is no problem, right? The Euclidean thing is, as long as in the Euclidean space, right, it's closed and bounded, is fine, right? Just anything that you do in general, there's no problem, right? So that's important formula that you will be solving, right? That's the important takeaway for this formula. Okay. And now we want to show you the case where we use it very often. Okay, is this following idea. Okay, how do you solve this model? Okay. And suppose they're going to divide the cake pie. So this means that the function, the set U, feasible set is a line, downward sloping line, right? And we are now what is the V, right? What's the U there, right? We will be talking the frontier. Why this is a frontier, right? So suppose V1, okay, maybe some typo here, let me see. It should be 1, so this should be 1, okay. So this is what V1 is the utility of 1, right? You take the inverse, give me the share of agent 1. You subtract the pi is what is left for agent 2, utility of agent 2, right? Is that clear? Is that clear what it says? Okay, let me repeat, right? V1 is the utility of 1, right? U1 inverse give me the share of the pi that agent 1 get. You subtract from pi, that is the share of the pi that agent 2, player 2 get. And U2 of that is the utility of the agent 2. Okay, okay. Let me do it slowly. V1 is V1 is just U1 x1. Is that clear? So I think that will be more clear, right? I should write that down. V1 is just U1 times x1, right? It's just U1 of x1, right? So just, okay. So why I do that? Because the efficient criteria just maximize a single variable, right? Of course, you can do conductor, right? Or Lagrangian the same, right? You can do Lagrangian, but what you show is you maximize this efficient, right? You just differentiate the product rule, right? This is the outcome, right? This product rule is fine, right? You differentiate V1, it's the G prime, right? You differentiate this one, this guy, right? Product rule, right? And you make this guy G, right? And the solution will be this one, and this is the solution, right? Right. So now this is general, but we make the case very simple. Okay. Usually we would do is risk neutral or linear, right? Which means this is the formula that you would often remember. Okay. Probably you forget about the product. This is the formula that you will remember when you apply. This is the formula. So the formula is like this. In the next bargaining, what player 1 and player 2 get is what? Is what they can get when they are alone. D1, D2, plus this bargaining surplus, right? They go together, get a pie. They do by themselves with D1, D2. So this is bargaining surplus. They will split equally. Can you see that? So this is usually a model that you would be using, okay? Because you are usually splitting the money, right? Assuming the money, basically you're assuming they are linear in the money, right? If you assume there's some risk aversion or diminishing marginal utility of money, you end up assume 0. This is what you get. There's some typo here. Okay, so some typo. Sorry, the typo. So that will be the result. Okay. And so you can see, but again, I want to emphasize this is the usually when you look at the literature or empirical literature, this is the next bargaining actually means this guy. So usually they will talk about this is the result, okay, and depend on D, that will be the outcome. Okay. Is that okay? But now I give you the foundation why next bargaining like this. Okay. So for the remaining time, I want to talk about other solution. Okay. But you don't really work too much, okay? Because they just replace it. Because as I said, IA is like controversial. So how if you try to weaken it or alternative one? So first we define what's the ideal point. Okay. Ideal point means that this is a point, okay, such that player 1 is the maximum possible they can achieve. Okay, just basically look at, if you are looking at the graph, you just draw the horizontal line until the end. That's the point. So basically like this, right? If you try to, this is the model, this is the set. Okay, you go to the basically just means the most right point. D may be somewhere here. Okay, as long as you try to draw a D here, write a D, D2 for the other guy, right? D2 for the guy, right? So suppose this is the point, is D2, right? D1, D2, right? And you draw the horizontal line there, right? this is the set remaining. Look at the one that x1 is the furthest, right? So basically, it's just like, look the case where above the disagreement point, right? What player 2 can accept, right? Cannot refuse. What is the maximum V1 can get? That's an ideal point, right? The best possible that player 1 can imagine, right? This is the best possible that, because you have to make sure the other guy accept, right? So basically, it's individual rational, right? Now, the second axiom, which I think is very natural, okay, is if consider two situations, U and U prime is smaller, we get it smaller, okay, and the ideal point is same for 1, okay, 2 cannot get more. So it means that A1 is ideally is still getting the same, okay, and what you can do is strings a little bit, okay, and U2 cannot be better off. Okay, you can imagine reverse. Originally they're the same, right? If they expand, they cannot be worse off. Okay, put it this way. Let me argue the suppose in this way. Let me draw it. Easy to think. So draw a line there. Okay. This disagreement points here. Okay. And you go this way. This is the maybe draw better, right? This one. And the ideal point is here. Right? Now you expand the set. Okay? So I don't know which point you pick, whatever point you pick, this is a solution, suppose. Okay? Now you expand your solution bigger. Okay? In the sense that this one remain the same here. See? I don't know how you expand. Okay? It means that player 2 cannot be worse. Okay? Players 2 must go up or go right. Okay? Because player 1, the best case is not improving. You improve other guy weakly, right? Then player 2 cannot be worse off. By allowing, imagine, right? Allowing a richer set of more alternatives, right? Adding more alternatives, okay? For player 1, the best scenario doesn't change. Player 2 cannot be made worse, right? Is that clear what it means? Right? Of course, it means also your strengths. It also weakly strengths, but same idea, right? Is that clear? So player 1, the best case doesn't change. You expand the set. Player 2 cannot be worse off. Can be same, but cannot be worse off, right? More opportunity. It is somewhat related to the IA somehow, but not exactly, because much more relaxed, right? IA require you string the set, the same solution, right? But we don't require the same solution at all, right? It's much weaker. So turn out that this solution is rather funny. Okay, the funny thing is, look, this one look crazy. Okay, this one look crazy, but I'm not going to. I draw a graph that will be very simple. Okay, you will understand what it said. It simply means the following. Suppose I have, this is U1, this is U2, right? And I have I don't know what the set is, so I should draw a convex, right? It's a set here, okay? And suppose the discriminant point is here. This is D1 and D2, right? And now you can tell me what is the ideal point here. Ideal point here go from this one, right? You cut this set. Ideal point is here, right? This is A1. And you can do the same here. The ideal point is here, A2. Right, so this is the hypothetical ideal point for both, right? So what the KS solution is very simple. I'm trying to do the following. I'm going to draw a line between the discriminant point and the ideal point. And the intersection of this point and the frontier will be our solution. The solution is this. Is that clear? So proportional to that. So that's what it means. Yeah, that's why you can see the proof say it's A minus D, the slope same as this slope, right? So that's that right? That is the idea. Is that clear? So of course, the math is slightly more tricky, but the graph is very simple. Right? The graph is very simple. Right, so that's what it meant, right? And of course, it can be shown this is the outcome. I'm not going to prove it, right? Because you don't really need to prove, right? But just showing you that you may consider this is the outcome, right? And I think that paper trying to justify why this is a good outcome, but it's not our goal to say why this is true. Okay. And finally, I want to have another rule. It's also very common. They call egalitarian solution. Egalitarian means equal, 平等, 平均, or 公平, or whatever you like, what the number, right? What is controversial here, right? And we replace it by using this, okay? Egalitarian point means, okay, all the points that give the same surplus to both. Okay, let's draw this. Okay, this is U1, this is U2, right? Suppose this is D1, D2, right? I want to look at the case, right? They're different, the same. What does that mean? What the point there? Can you imagine? It's a 45 degree, right? Because, right? But do note that this is only focused on, you have to draw a set first, right? So suppose this is a set, right? E1 will be, all the points will be within the set, right? So basically, go down here, this is the set, right? And for player 2, that will be somewhat here, right? Is that clear? Okay. Now, once we have that, all the point that means that they have the same surplus, right? And egalitarian would be just what I said, right? You draw the 45-degree line and just cut it, right? I think that would be something like that, right? So instead of this A1, A2, right? You draw a 45-degree line, maybe somewhere here, right? This will be the egalitarian. Right? Is that clear? So if A1 equal to A2, then the same result, right? So if they're symmetric, then it's egalitarian will be the same as the KS solution. And egalitarian is very simple as well, right? And you can see if they're symmetric, the next bargaining solution is the same as the egalitarian, right? If you talk about you're dividing the money, right? Because look at the case, go back to this one. If D1 equal to D2, right? That's what you expect. Draw a line there, go to the 45-degree line, same. Right? And if you, the same result, right? If this, the KS also the same thing, right? If symmetric. So if they're symmetric, that's actually the free solution, same thing, right? But if they're asymmetric, the free solution differ. Depending on how the opportunity set is different, right? Everything can be different. Okay, I will talk about this strategic form after the break. But here we are finished everything, right? We know next bargaining solution, egalitarian, and KS solution. But mainly you will remember as you apply, you would just, I would say, most of the time, this is the formula you need. Right, this is the one. I mean, in most applications. But of course, you can add more crazy stuff there, but if sometimes this is very difficult, right? Then you can use the other solution, right? The KS solution or egalitarian, also fine. And some of you may think this is something crazy. Egalitarian is never happened. In fact, some of the experiments show egalitarian actually may predict things better in some time, because people in some case worry about justice and fairness, and these actually predict better outcome. So it's not entirely clear that people are so strategic. Okay, at least in the real world. In some cases, if the stake is not too large, then equal outcome might be a little bit something you predict, right? Not exactly as the game theory predicts. But anyway, we'll talk about this strategic form after the break. Let's a break of 15 minutes. We'll resume at 4:40. ideal point 代表我拿到的东西，所以就是对于那个 next bargain compare 这个 ideal point。这个为的 ideal point 是个数据 ，ideal point 都是有的 ideal point 都有表达了一个 bargain 的 process， 他们两个那个是最大的。比如说我们价值的多，设计的多一点，做到我们所以你认为，但是你当我们的 ideal point。
说你有什么能力，在这个 collaboration，我的好处，我可以 manage more，还是 have more。对，比较像你的可以活动的好处比较多，所以我应该对某程度上有点高高，就是达到依照多少分，但是我可以获得更多的好处，所以 more alternative than benefit me， but in choose it， so I sacrifice a lot to pay me。这个在跟你说，如果拿你的吵架，说我让你杀了你，看了你，把他高富帅给有去过的。
生动的例子，对。
对，我就这样子嘛，他跟你说，当年高富帅有去过的。
你们这边吵架还是这么吵？
没有。
我感觉这个吵。
我举个例子嘛，对吧？就这个例子，你跟你说，哎，当年高富帅有去过的，所以你打多一点。我那挑了你，让你杀了。
有一部那个档次不是说什么欺负呗什么的。对，我也看过这个。
所以就这个意思。人家说你说管理的高富帅都没有找他，就是不用管，都没有。沉默了嘛，对吧？你没有管他，你没有叫他，没有他的影响，没高，对吧？
该说这些也没有用。
对呀。
那应该是 Karen。
这个 Karen 就是说，就是我们管理以前什么东西，我们现在就公平分，管理有别的东西没所谓，跟这个没关系。一偏一半，对吧 ？B.B.A. equals B， 不管你有没有别的高富帅，反正我们的分，对吧？3分的分对半。看你就是什么 model 有个 market， 偏好高，看你觉得怎么把它的模式。
是要根据现实这个问题。
其实结果一个什么样的结果，我也看接近什么样的关系。所以，我觉得就把门口的天天用，可以用的啊。说不多的钱啊，合作那种可以。就是我跟你的合作怎么跟你的情况是这个 division 怎么看的，比如说 joint venture 怎么看的，
那现实生活中他真的是这么决定，还是说是公平的？
我觉得这个比较合理，但是这个合理是真的，我不能花去说话的，因为我们呢，我会给你的话，我们假定这个结果，我们都有个合理，但这个结果是可以永远实现的。
但是是不是要讨论他为什么没有拿到这个结果？用这个去
所以在学这个，所以这个做比较实际嘛，对，这个的话，你改变点就不一样。
对，然后再看到底在。
对了，所以就是这个是 general 就解决这个，所以这个是属于 reduce， 所以我发现说这个是 reduce form， 你可以大概看成，如果没有什么特别的话，特别的话就来解决另外一种。
可以留待有空可以交流一下。 So let's talk about strategic bargaining. Okay, so this literature is super huge these days because of the way that you can model how they interact. Okay, of course, later you will see. Okay, now we talk about the game that's Nash start. Okay, Nash basically talk about how to justify this game, right? What might be the outcome? Okay. So consider the case the Nash called Nash demand game. It's also in the same paper. You consider a case where they simultaneously move complement game. It's a cake of size 1. So 2 players propose a division. Okay, division can be add up to 1 or nearly up to 1. But anyway, just put any division. If the division is compatible, they split. Otherwise, they flow into water. Right? Just say player 1 said half and half. Player 2 said I got 2/3. You get 1/3. Then the cake is flow in the water. Okay. And in this game, you can see any division compatible that is equilibrium. Same as what we see in the double auction, right? Say buyer and seller limit price, right? As long as the price is compatible, there's a solution, right? And this actually doesn't single any equilibrium, right? Because any outcome is multiple equilibrium, right? But at least as a first way to say, okay, any possible outcome is there, right? Because in this model doesn't tell you anything, right? Just tell you that, okay, we have a division that is Pareto optimal, right? But doesn't tell you anything, right? Any division is outcome, okay? So it's not really ideal, but at least you can say there's a strategic element there, right? There's a way to decide the division, but they just say it's indeterminate, right? Because every outcome is possible. It doesn't say anything, right? Doesn't even know, right? Doesn't, because Nash bargaining tell us a particular point there, right? KS solution or egalitarian tell us a particular solution, but this one no, we don't know which solution there. But anyway, doesn't really matter. Let's go next. Let's tell you a game that tell us one solution, okay? One equilibrium, unique equilibrium, okay? Instead of simultaneous, we allow sequential, okay? Now, they divide $. Player 1 will say, I propose we divide $1 in this way, okay? Player 2 said, only have 2 choices, take it, divide accordingly, reject, the money fall into rubbish bin, okay? So this is similar to Nash bargaining, Nash game, Nash demand game, but the player 2 just say yes or no. Player 1 propose, and player 2 say yes or no. Yes, divide, no, fall in the bin, okay? And you can imagine what is the equilibrium? Equilibrium would be saying player 2 would accept anything, right? Because if you don't accept, it's 0. Right? Accept anything is at least 0, right? You'll be okay. So then if player 2 is accepting anything, player 1 will propose barrel induction, nothing to player 2, keep everything to itself, all right? So that is the unique equilibrium there, okay? And is it going to be the outcome? Okay, is it the case in the real world? In experiment, seems to be you would be saying that no, because people have kind of self-image, or kind of like, I have underlined the bottom line, you give me less than half, I just throw away. I rather destroy it because I feel unfair. I don't even value the $. You give me so little, well, no, nothing, I just throw away, rather throw away, right? But in business world, then of course this might be reasonable, right? That's what happened in the world when the proposer is the firm, the receiver is worker, right? Probably you know what happened. In many cases, the firm said, okay, there's a job there. I give you $1,000. You do it or not? You don't do it, then no job. Right? That's what happened. Right? You have to do it, so you do it. Right? But that's what happened, right? There's a case where the firm actually exploit to the utmost. Right? That is what the in your old day, right? They call it evil capitalists, right? Extract as many surplus as they do, leave nothing to you. Right? That's what happened. Right? But it happens in some scenario, right? Just I try to grab everything there, right? That's what the old story, the Aesop fable, right? What they call lion share, right? I don't know whether you know the story, right? The lion go hunting with a deer and another animal, right? The lion, they finished hunting, they got the animal there, and the lion said, okay, because I am the leader, I should get 1/3 of the share, right? And I'm stronger than you guys, then I get another 1/3. And the other share, if you touch it, you will be dead. So you get everything there. That's called the lion share story, right? That's what actually happened here, right? But anyway, now let's consider a game where a little bit more realistic, okay? Consider the case where we have what we call two-period bargaining. How does it work? Player one, make a proposal to player two. Player two say yes or no. If player two say yes, then they divide accordingly, game over. If player two say no, the game go to the next stage, next period, okay? And next period, now it's the turn the player two to propose. Player two propose, okay? And to player one. If player one accept, then it's over. If player two reject, player one reject, also over. But after one period, the cake shrink by delta, okay? You can imagine that they're cutting ice cream, okay? After a period, the cake melts a little bit. The ice cream cake melts a little bit. Or because of waiting, okay? They just reduce by delta, okay? So is that clear what's going on? Okay? So how to solve this game? Again, double induction, okay? Look at the period two. Period two is what? It's exactly ultimum game, right? Player two just propose whatever, player one accept. Last period, right? So player two will propose what? 1, right? And player two payoff will be 1 here, player one will be 0, right? But now go back to previous stage. Look at what player one can propose to player two, right? Player two at most get 1 in the next stage, right? So as long as I give him delta or more, which is the cake melts, the most is the delta in the next period, right? So I give you delta, you accept, right? So the outcome would be player one will get 1 minus delta, player two will get delta. That will be the only sub-game perfect equilibrium. Is that clear? So that would be the outcome. Okay, so do note that is immediate agreement. Player one propose this, player two accept this, and player one propose 1, player one accept anything. Okay. Do note that the sub-game perfect equilibrium, you have to tell me the strategy. Okay. Of course, the outcome is player one get 1 minus delta, player two get delta. But the equilibrium have to be the strategy for each round. Okay, have to be distinguished that the sub-game perfect equilibrium is the strategy for each round. The equilibrium outcome would be player one get 1 minus delta, player two get delta. Okay, is that okay? Is it clear how we solve it? Okay, so now you can imagine that we can go one step further, right? Suppose free period. What you will see, okay? 3 or more, okay? Look at the third period, okay? Third period, we will just give, player 1 will give player 2. Player 2 can at most get 1 minus delta, right? Okay, put it this way, right? Because if you are the proposer, okay, so this offer this to this guy, right? So you just need to offer this much, except. So basically you offer, let me see. Okay, put in, let me draw it, maybe easier. Barrel induction, right? Player 1, player 2, player 2, player 1, player 1, player 2, right? So player 1 would simply say, okay, I give you 1, 0, you accept, right? It's the offer you will see, right? 1 is player 1 get, right? And player 2 in this case would just give player 1 delta, right? He keep 1 minus delta, will be the equilibrium that player 2 proposed, right? And player 1 will simply give player 2 delta, 1 minus delta, right? And 1 minus this guy, right? So as long as player 2 get delta, 1 minus delta, player 2 accept. Is that clear? Is that okay? So this is saying that this part is the one that give player, right? And so on and so forth. You can show that this is the outcome if you do more than n, okay? But anyway, you can just take n to infinity, right? And that is the 1972 paper, tells you that this outcome, okay? And when this go to infinity, right, you can see what you would get is player 1, the proposer, will get this much because this go to infinity, right? Okay. Player 1 would give this to player 2, okay? And player 1 would get this much. So division like this. If t go to infinity. Okay, because this is, okay. Okay. So being the first mover, you get some advantage, right? Because this is bigger than this one. Okay. And if you take delta to 1 and go to infinity, that means that everyone get half, right? Which is same as what the Nash bargaining solution or what other solution is, right? So, and okay, that's why most of the paper will assume, you will see, they just say, assume Nash bargaining, they split surplus. Okay. And of course, here I don't have the D is 0 here, right? If I allow D is different, okay? I can also get the next bargaining solution, right? But I don't want to talk about those. It's a little bit more complicated. But you can modify the game such that you get the next bargaining solution. So there's some way to modify the game such that the subgame perfect equilibrium is this one. Is this one. Okay. But you have to modify the game in a certain way to support this guy. So I'm not going to talk about those. Okay. But what I want to mention is what Rubinstein proved. Okay, this is the result, which is same as what we take t to infinity. So why this paper is very famous is because previously we just take n to infinity, t to infinity, right? But that's a limiting case. But this is what Rubinstein proved is consider the game as a repeated game, right? That means that you cannot do backward induction. That is why this paper published in Economic is so important paper. You can check it out. It's very fun to read. It's a very neat paper, and you will see his model is much more general than we are doing here. But at least the most important part is he showed that even in this game, it's a repeated game, even a game, not a game, even a game, right? Because they can bargain until infinite, right? It can never end. But turn out that he can prove, okay, the subgame perfect equilibrium is unique, which is surprising, because you can imagine when the game plays continuously, there can be many outcomes. Look at the game literature, right? And it's surprising that turn out that you can prove there's a unique equilibrium. Regardless of how you think the model, they interact infinite period, right? But turn out the only outcome you can see this one, right? Because if you look at the game theory literature, you will see when the finite is not very well, when you go to infinity, can be expanded, equilibrium set can be much more. Okay, there's no guarantee that when you expand to finite to infinite, still a unique solution. Can be one of the solutions, but the important point is he proved that even though to go to infinity, only still one solution. So that is the part that people always talk about Rubinstein bargaining, what is style bargaining, because Rubinstein actually proved it very strongly. Okay. Okay. Is that okay? So now, because this is so important, let me define the model formally. Consider case we have two players, the cake of size pi to be divided, and even period, that's standard way. You start from period 0, that's a way the bargaining people do. Even period, pair 1 make offer, pair 2 make in the odd period. Okay. And the share is discount by now different discount factor. Right? Player I have delta I. Okay. And this agreement means they go to infinity, that will be 0 payoff. Okay. Now, how do we prove that? Did I prove it? Okay. I'm not going to prove it. It can be shown, okay? The equilibrium like this. Firm 1 will get this much, firm 2 will get this much. Okay? The denominator for x1, x2 the same, right? And how much you get, x1 get, depend on patient, right? So you do this. It's easier to look at the relative. x1 star over x2 star is what? is 1 minus delta 1, delta 2 over 1 minus delta 1. Okay? Which means what? If delta 2 is the patience of the player 2, if they get more, player 2 get more patient, means delta 2 goes to 1. Bigger, player 1 get less. Right? If other way around. So who is more patient will get a larger share. Right? That is very simple, right? Because you can imagine, right, when you're bargaining, right? Patient means how long you can wait. Right? You can wait long enough, then you can get larger, right? You can hold out, right? Because if you don't collaborate, you get 0. As long as I have deep pocket, I can wait. Then you win. Right? That's why men don't want to get married or want to delay, because they can wait. Right? The waiting for women is more costly, right, in general. Right? So that's why, and it's getting more costly, right? Getting more costly than costly, right? So that's why men want to wait, don't want to get married, right? Because until that woman can't wait anymore, then he can get larger surplus, right? Right. That is, some people did that, right? Many men don't want to get married, right? Because they want to wait until the woman become impatient, right? And then get large surplus, right? And then that's why there's a saying, right? When men and women more than 30 years old, it's very difficult to be in the dating market, right? And when you get more than 40, then it's more difficult, right? Because you're getting more impatient, right? But anyway, whatever, none of my business right now. Now, so as I said, this is the equilibrium. So this is one they use, right? That is slightly different from the net bargaining, right? Net bargaining only says your payoff depends on your disagreement point, right? Doesn't tell you how long you can wait, right? But by modeling the process, how the waiting, actually the time preference, the patience change the outcome, right? It's not about the disagreement point, right? It points out one thing is how long you can sustain, right? How long you can wait until you resolve is important, okay? Of course, when we say net Rubinstein bargaining support net equilibrium means we can actually do that, okay? With a D here. Okay, because what we mean by disagreement point? Disagreement point means if you don't successfully negotiate, then you get D. Right? So we consider a case where there's some probability P that will break down, okay, every period. Okay, like we bargain, so pair 1 make an offer, pair 2 accept, ends. If pair 2 reject, nature decide you continue or not with probability P. It's P. Yeah, probability P that ends. Okay, 1 minus P continue. Okay, so in that case, you can see, okay, the outcome become, make it simple, but assume delta go to 1. That's what you get. All right, and look at the case when P go to the breakdown is go to 0, almost go to 0. That what we get is net bargaining solution, right? Exactly, net bargaining solution, right? So that's why we say there's some support for net bargaining solution. If you assume this is the model, right? You assume people are patient enough, the player are only different by their disagreement point, then the risk of breakdown is like this. That's a net bargaining solution. Okay, of course, different bargaining solution you can write up the model to support it, right? That is what we call the build the foundation for that, micro foundation, right? But you can see, okay, how you model this, right? If the next solution is there, right? So that's why we can safely use next bargaining solution if you believe that this is the way people bargain, right? People give an offer. If offer doesn't work out, they break down. Okay, you can imagine breakdown is like also option, right? If someone comes in and break it, right? It's like the boy and girl are negotiating this how to split the surplus of marriage, but sometimes someone come in, another boy and a girl comes in, they will break down, right? They're not getting married. They marry some other people. The payoff is D. That's what they get. Okay, is that clear? Now, let's break down. So, what I want to mention is another important principle in bargaining, okay, which is in the next slide. We call the outside option principle, which is something very later you agree with me. There's something very interesting thing. Is you assume if I reject the offer, I can get the EI. Okay, suppose this is EI, maybe the firm and worker bargaining. Okay, EI may be I get a job from somewhere else, right? And the firm can get surplus E2 from hiring another guy. Okay, and they still keep talking because they figure out that the joint outside option is less than what they can get, right? Otherwise, they would not talk, right? Is that clear? What is it? So the game is just like no breakdown, but just say they bargain. I give you an offer, you can take it, it's done. You don't take it, you can take outside option. Okay, you get it. Okay, and in that case, okay, we will have some what we call in this case we call outside option principle. Okay, it means that as long as E1 and E2, okay, are smaller than this two number, is not useful. Okay, so that's what happened. Imagine you're working for a company. You're making salary of say whatever number, okay, maybe X, okay, and you say someone want to hire me for X minus $1,000. Okay, suppose the case. Okay, suppose you're working for a company. You are working for like $1 million. Okay, $1 million annual salary. Okay, and you say, okay, you talk to your boss. Can you increase my salary? Someone pay me $900,000. I said, the boss said, go away. I don't care, right? As long only the option is only useful when the option is more than what you're supposed to get, right? So that is what outside option principle, right? So that is what you get is here. Just like this, okay? If your outside option is not more than half, right? Game proceed as before. If your outside option, typo. I'm so sorry. Okay. If player 2 option is useful, you will follow 2, right? Otherwise, follow 1. Okay. And then this will be the outcome. Okay. So only the option is only useful only if you may ask when is 2 side will be more than no, because if 2 side more than they will not talk anyway. Right? So we assume E1 plus E2 more than pi, so only 3 scenario. Okay? So right, you can see outside option with the bargaining very simple, right? If outside option, then outside option will be the outcome. Right? So actually make this make the model more simple even. Okay? And you can see this M&A thing, right? Very often, or the other option, make the model even simpler to solve. Okay. So I just very roughly talk about this because it's a little bit more complicated. Here is, instead of saying player 1 do first, player 2 do second, each, and then 2-1, 2-1 is the deterministic. Every round is just toss a coin. Decide who is going to propose. Every round toss a coin. If head, I propose. Tail, you propose. Okay? So that's the P. Obviously, there's a typo again. Sorry. This will be 1. Okay? And I'm not going to tell the proof. Okay? The result is like this. That's what you get. Okay? This is the equilibrium result. Okay? That's basically 1 minus delta P2, and this is the result you get. Okay? And you can imagine that delta go to 1, P1 equal to P2, then X1 get half, right? And X2 get half, right? So that corresponds to what we have, right? But that, why we need that? Because P1 and P2 represent what? The idea of proposing right. Who has the right to propose? Is the proposer has a lot of power, right? Because you can see that it's decreasing in P2, right? P2 and P1 plus e to the 1, right? Who can say first is very important, right? So that's why look at the US, right? So often look at who is the speaker is very important. Look at the Congress, right? Because speaker or the leader actually makes a proposal, right? You're only allowed to say yes or no. It's a different, or who makes the proposal first has a lot of power, right? Because he decide what to be discussed, right? Because who set the agenda is very important, all right? Not going to go to the many things there. I don't want to go to detail. This is related to some papers that I do 2 years ago. So it's related to what we call one-to-many bargaining. Okay, so far it's 1-to-1. Okay, the first thing you probably want to do is, what is the result when you extend to more than 1? Suppose 4 of us here, going to divide a cake, divide $1. What is the solution? Okay, the answer is, unfortunately, anything is solution. Okay, but first, one thing I have to mention is, if suppose 4 person or 3 person to discuss to divide $1, you have to think about, because I suppose 3 of us, I propose the division among 3 of us, and what we require this agreement to be accepted. Is it going to be unanimity, right? If this agreement will be accepted if everyone agree, or this called unanimous protocol, or we only require majority. If 2 persons agree, then we're done. Okay, that is we call majoritarian bargaining. Okay, and turn out that no matter what you use, okay, basically any outcome is like Fock theorem. Any outcome is possible. Okay, and that means that we don't have anything to say in general what we have in the what we have in the bargaining, unlike 2 persons. So that's what. But before you get unhappy, one thing I would want to say is, even though this will still hold, okay, this next bargaining solution will still hold as the unit stationary subgame perfect equilibrium. Okay, if you require every agent use the same strategy every period, okay, no matter how long it passed the history, then the unit stationary subcapital net equilibrium will be same as the net bargaining, like this one. Everyone get 1 over n of the surplus. Okay, so that's usually how we do in the practice. We just do net bargaining because it still stands as the nice outcome. Okay, free bargaining here, right? More than that, the problem is when you have more than 5, okay, it's majoritarian, and if you have that means that you don't have any nice outcome there. Okay, and this is what they call the multilateral bargaining, and another bargaining that I work on is called one-to-many, okay, which is very useful when you talk about a firm is talking to worker. Worker themselves don't bargain, right? Firm talk to each worker, and they jointly come together to do the production, right? But worker don't talk about each other, right? Or the land developer try to collect lands from each owner to build a project, right? But the farmer doesn't talk to each other, right? So that's one-to-many, okay? And there are many models that we can do, and it can be shown, okay, if you do some protocol, okay, and the solution can be used what we call the Sharpe value. Okay, I don't have time to talk about Sharpe value, but if you have time, you can check what a Sharpe value is. The Sharpe value is that by default is called the average marginal contribution. Okay, okay. But let me talk about what is the Sharpe value at the end, in case you want, because in the empirical work, usually when we talk about firm and the worker, they assume everyone got the Sharpe value. So what is Sharpe value here? I just very briefly talk about. Okay, Sharpe value is like this. Okay, you consider the surplus of free agent. Okay, you consider the case if only one guy is here. Okay, how much the surplus they can produce. Okay, and any subset of agent I can look at how much surplus I can produce, right? Imagine I'm a firm, I don't hire any worker. How much profit I can produce? Okay, maybe the owner just work by himself. Okay, and look at the case, I hire a guy number 1, how much surplus I produce? And look at guy number 2, how much surplus I can produce? Okay, what is average marginal product? Okay, in this case, look at the scenario like this. Okay, it's like this. Okay, look at the case where there's nothing here, empty set. Look at the case when 1, how much the social surplus increase. Look at the case when we have number 2 guy here, become 1 and 2, how much the surplus increase. Look at case 3, it become 1, 3, how much 1 increase there. And look at the case 2 and 3, become 1, 2, 3, how much the surplus increase, right? For free agent, only these cases, right? And player wants to get average of this outcome. Look at free agent, everyone will get the average of those. Okay, that is called the Sharpe value. Okay, I'm not going to talk about that further. There is a way to show this have a nice property there. Okay, it's similar to net bargaining, right? Sharpe value is another way to division of surplus. Okay, but you can check the textbook or whatever, but that is a very famous concept. Okay, And it also with the core. Okay, remember the core we mentioned in the general equilibrium. Okay, when the game is convex, set p-value is in the core, so particularly in the core. But anyway, in the literature, especially empirical literature, when we talk about one-to-many bargaining, okay, set p-value is the way people talk about. It's the way to solve the problem. Okay, because net bargaining is not really that realistic in this kind of model. Okay, so people use set p-value when you talk about one guy talk to many people. Okay, so I guess overrun by 3 minutes, but I guess that's conclude our class. So good luck, Merry Christmas. Remember to submit your project after Christmas. Okay, I'll see you. Bye bye. Have fun. See you. Bye bye.